This seemed to be the problem that people had the most difficulty with on the test, the free body diagrams in problem 1. Let's have a look at it. So we need to sketch and label the section free body diagrams and show the external load and the internal loads and the stress area with dimensions. And then write the equations for the stress in terms of the dimensions, and the dimensions are A, B, T, and D, and the external load, which is F, as well as the reaction loads. If there's the external load F here, there must also be reaction load at the bottom of the clevis, also equal to F for what it's worth. There must also be a moment operating this way at the bottom of the clevis. That doesn't really concern us much for our stress calculations. So the normal stress in the bar, not at the hole, but anywhere along its length. So you have to kind of be clear about where it is that you're going to put the section. I'm going to make mine right about here and keep it simple. And then the diagram is, I'm going to take everything to the right of that section. Here's my section. Here's external load F. There must be also a load here, an internal load. I can call it P, or you could call it F. And also you're meant to draw the stress area, the total stress area. And this has dimensions AB. Well, because of equilibrium, F and P are equal. The equation for stress is P over A, and in this case, the area is simply AB. So the equation that we're after is the stress in the bar is the external force F, which is equal to P, over the area, which is equal to AB. This is what we're after. For bearing stress in the clevis, well, the clevis is that whole assembly. It's both of those ears, or those things with the pin in it. So you have to figure out how to best draw it for bearing stress. Clearly, the bearing stress happens kind of in the holes here and on the other side. I'm going to do a top-down view to show this. Here's the hole. And we have the reaction, ground reaction force, F, pulling back this way. So there must also be a force pushing on the inside here and here. I'll call that P, the bearing load. And the areas that matter are the projected rectangular areas inside the holes. And they are T by D. So again, the internal load is balanced. The external force equals the internal bearing force. The area is the area of two rectangles, 2 dt. Bearing stress in general is the load over the area, the bearing area, which works out to being F over 2 dt. That's what we're after. Finally, for shear stress in the pin, well, I'm going to draw, again, the sections we're concerned with are kind of, well, you can't really draw it easily on three-dimensional drawing. But again, from the top down, with sections through the shear interfaces of the pin, let me see, here's the bar with its external force F. Here's the pin, and there must be the shearing force V, I'll call it, the total shearing force V, on that cut face. And again, there's two of them. There's diameter D and also diameter D. So again, the balance of forces, the one that I like best is F equals V. I don't like to do it half and half. You could say that you could call V the shearing load on just one of the areas, and then V would be a half F, but I kind of prefer this method instead. The area is the area of two circles, so it's 2 pi by 4 d squared. And shear stress, tau, not sigma, tau, it's V over A. But that works out to be that the shear stress is the force over, well, if you could just leave it as 2 pi by 4 d squared. I did say simplified, so slightly better answer would be the simplified version of 2f over pi d squared. This would have been okay if you'd left it at that as well. I hope this helps. This business of drawing section free body diagrams and being very, very clear about what the forces and areas are, it's an important kind of foundational step in order to understand what's going on with stresses caused by these internal loads. I hope that helps.